Patterns in nature. Patterns govern structure throughout nature. There are recognizable patterns in plants and trees, like patterns of proportion in size, patterns in placement of leaves, patterns in the number of leaves, petals, seeds, etc. Patterns in shape of flowers, vegetables, fruits, seeds, etc. In fact, there is a definite geometry at work where patterns are concerned. Patterns in number and arrangement of petals. There is in geometry a well-known golden ratio of 1:1.618. There is supposed to be the most economical ratio of growth in configuration of geometrical forms. In nature, we find that the golden ratio is not an absolute, but a proportion that tend towards 1:1.618. If you are asked to draw a rectangle that pleases you, it is most likely that the ratio of its length to width will be a golden ratio. An interesting progression of golden ratio is Fibonacci numbers. That refers to the series of numbers where each number is a total of two numbers preceding it, and the ratio of two consecutive numbers is the golden ratio, such as 1, 2, 3, 5, 8, 13, 21, 34. The Fibonacci numbers and golden ratio are widely found in the plant kingdom. In nearly all flowers, the number of petals is a Fibonacci number. Non-Fibonacci numbers do not occur often. For instance, very few plants have 4 petals, some exceptions being fuchsia and mustard. Some plant species such as buttercups are very precise with regards to number of petals they have, but with others only the average number of petals is as Fibonacci number. Probably most of us have never taken time to examine very carefully the number or arrangement of petals in a flower. If we were to do so, several things would become apparent. First, we would find that the number of petals on a flower is often one of the Fibonacci number. One-petaled flower, as in white calla lily, and two-petaled flowers, as in euphorbia, are not common. Three petals, as in trilenium, are. There are hundreds of species, both wild and cultivated, with 5-petaled flowers. 8-petaled flowers are not as common as 5-petaled, but there are quite a number of well-known species with 8, 13, 21, and 32-petaled flowers are also quite common. The outer rings of ray florets in the daisy family illustrate the Fibonacci sequence extremely well. Daisies with 13, 21, 34, 55 or 89 petals are quite common. Ordinary field daisies have 34 petals. In saying that daisies have 34 petals, one is generalizing about the species, but any individual member of the species may deviate from this general pattern. There is more likelihood of a possible underdevelopment than overdevelopment, so that 33 is more common than 35. Patterns in number and arrangement of leaves. The association of Fibonic numbers and plants is not restricted to number of petals. New shoots commonly grow out from the stem from a point in the axil of leaf, as we can see in sneezewort plant. If we draw horizontal lines through the axil, we can detect obvious stages of development in the plant. The main stem produces lateral branches at the beginning of each stage. The lateral branches rest during the first two stages, then produce new lateral branches at the beginning of each subsequent stage. The same law applies to all branches, since this pattern of development mirrors the growth of the rabbits in Fibonic's classic problem. It is not surprising that the number of branches at any stage of development is a Fibonic number. Furthermore, the number of leaves at any stage will also be a Fibonic number. The type of growth exhibited by the sneezewort also occurs in simple tree growth, each stage of development lasting 1 year. The schematic diagrams of the sneezewort tree have been presented as though the plants were flat. This illustrates the development which leads to Fibonic numbers, but it suppresses the characteristics of a majority of plants, where successive leaves or shoots spiral around the main stem with successive stages of development. Suppose we fix our attention on the leaf at the bottom of a stem, on which there is a single leaf at any one point. If we number that the leaf as 0 and count the leaves up the stem until we come to the one which is directly above the starting one, the number we get is generally one of the Fibonic sequence. Again, as we work up the stem, let us count the number of times we revolve around it. This number 2 is generally a number of the sequence. The arrangement of leaves can then be expressed as a ratio. The number of leaves in our sample plant is 8 and the number of revolutions 5. Fibonic numbers are often found in the arrangement of branches, leaves and seeds. If we look at a plant from above, the leaves are not arranged directly above one another, but in a way that optimizes their exposure to sun and rain. The Fibonic numbers occur when counting both the number of times we go around the stem from one leaf to the next pattern in arrangement of florets, seeds and fruits. With the scale pattern of pine cones, the seed patterns of sunflowers and even the bumps on pineapples, we have something rather different. The seed-bearing scales of a pine cone are really modified leaves, crowded together in a contact with a short stem. However, we can detect two prominent arrangements of ascending spirals growing outwards from the point where it is attached to the branch. In the pine cone picture, 8 spirals can be seen to be ascending up the cone in a clockwise direction, while 13 spirals ascend more steeply in a counter-clockwise direction. In the close-packed arrangement of tiny florets in the core of a daisy blossom, we see the phenomena in most two-dimensional forms. The eye sees 21 counterclockwise and 34 logarithmic or equiangular spirals. In any daisy, the combination of anti-clockwise and clockwise spirals generally consists of successive numbers of the Fibonacci sequence. Pineapple scales are also patterned into spirals, and because they are roughly hexagonal in shape, 3 distinct sets of spirals may be observed. One set of 5 spirals ascend at a shallow angle to the right, while a second set of 8 spirals ascends more steeply to the left, and the third set of 13 spirals ascend very steeply to the right. Pentagonal indications are seen at the bottom of the fruit. Cutting the apple in half reveals a star pattern of seeds. Patterns in vegetables and fruits. Cauliflower. An ordinary cauliflower is almost a pentagon in outline. Looking carefully, you can see a center point where the florets are smallest. Look again and you will see that the florets are organized in spirals around this center in both directions. Each floret is peaked and is an identical but smaller version of the whole thing, and this makes these spirals easy to see. Have you seen and observed the shape of lady's finger, bindi? It has a 5-sided pented shape. So does a banana, kela. Look at a raw banana. In fact, the banana in cross section has a triad in the center, 3 sections.